Okay, cool. And actually, I do need to take attendance. Let me take care of that really fast. Everyone's here. 5, 9, 12. Cool. Sweet. All right. Yeah, so that's what's happening. So now going back to the answer key for the homework. Um, obviously, if you plug in 0 for theta, because that's where you start, you should get 1 minus 3 minus, sorry, 1 minus 3 times 1, which is -2. Now be careful about this, because if I plug in, actually, I'll go back to the homework. So it's 0 radians right here. So if R is 2, I'd be right here, right? If R is not 2, it's -2. So that's why it flips, starts there. So that's the starting point right there. And if it's going clockwise or counterclockwise, well, when I saw the graph, and I saw it do it slowly. By playing, like, say, pi over 6, pi over 4, pi over 3, pi over 2, whatever, it did this, right? So that's going counterclockwise, right? It's going from here to here. And by the way, when does it hit the pole? If I make a little table, which is, I would strongly recommend, as you're just getting used to how these graphs look, it might be a good idea to make a table of theta and r. Like, theta is like your input, r is your output. And I know when theta was 0, I got -2, right? That was pretty easy. From R value. Now, when theta is pi over 6, it's still gonna be negative. Now, pi over 6, what's cosine of pi over 6? And so if you do 1 minus 3 times root 3 over 2, so I'll just write it out in all its glory. 1 minus 3 times root 3 over 2. Now, we'll do a little mental math. Root 3 is 1.7. Times 3 is 5.1. Divided by 2 is 2.55. 1 minus 2.55 is -1.55. So pi over 6 is right here. Raised to 1, raised to 2. So it's probably somewhere over here between 1 and 2, but it's negative, so it has to flip. So it's actually over here. That's really where it is. If I do pi over 4, you're still going to get a negative r value, right? 1 minus 3 times root 2 over 2. What's root 2? 1.4. What's 3 times 1.4? 4.2. What's 4.2 divided by 2? 2.1. What's 1 minus 2.1? -1.1. So if I'm at pi over 4, I expect a radius between 1 and 2, probably closer to 1. But because of negative r value, it's going to flip over here. See how that point gets generated, right? So that's how I would graph that by hand. If I do pi over 3, that's an easy one. Cosine of pi over 3 is what? So 1 minus 3 times 1/2, which is -0.5. So if I look at pi over 6, which is over here, raised is 0.5, sorry, -0.5, but it flips, so it's going to be right there. Now, if I plug in pi over 2, this is the part I really want you guys to be present to, what's happening between pi over 3 and pi over 2. This will help you get a better understanding of how this graph is generated and when it touches the pole, or when you have zeros of the polar curve or polar function. Pi over 2, what's cosine of pi over 2? So 1 minus 3 times 0, which of course is just going to be 1. So if this were -0.5 at pi over 3, the r value is 1 at pi over 2. Between pi over 3 and pi over 2, I expect r to equal what? Would r equal 0? Yes, exactly. R has to equal 0 in between these two values. Pi over 3 is roughly 1.05. Pi over 2 is 1.57. So when I solve part E, when I ask for the zeros of the polar function, I'm going to expect the answer somewhere between pi over 3 and pi over 2. We'll do that in a moment. But clearly, just based upon how the points are being generated, it's going like this. If I use a laser pointer, it's starting here. It's going counterclockwise until I hit the pole. And it keeps going counterclockwise when there's the outer loop, finishes off the outer loop, and then finishes off the inner loop. This is what we expect to happen, right? So, Sophie, go ahead. Look at the graph. You want to see what the calculator is doing. I mean, if you plot the points, you can see for yourself, right? As you plot points, I would strongly suggest doing from 0 to pi over 2, just so you have a good feeling what the graph is doing. I was trying to suggest that. That'd be my recommendation. Now the symmetry is easy. We talk about it. Just replace theta with negative theta, see what happens. It stays the same. So that's symmetric about the polar axis. Polar axis is horizontal, or theta equals 0. If you say symmetric about theta equals 0, polar axis, both are acceptable. To show it algebraically, you got to replace theta with negative theta and see what happens. If it stays unchanged, great. It's symmetric about theta equals 0. If r goes from if r changes to negative r, then it's symmetric about theta equals pi over 2. Remember, there's another way you could verify by doing pi minus theta. Sometimes we might need that. We'll worry about that later. Sometimes it may not be obvious, but we'll see it when we get there. Okay, for part E, when asked to find the zeros, literally replace r with 0 and solve, and you have to use your calculator. When you do inverse cosine of 1/3, you will get 1.23. Now, 1.23 is in the first quadrant. It's not quite to the positive y-axis because that's 1.57. So I also expect this to happen, negative 1.23, which if I go counterclockwise as a positive angle, do you guys see how I got 5.052? Because that's 2 pi minus the reference angle, minus 1.23. Now, 1.23 is definitely between these two values. That makes sense because the r value of pi over 3 was negative 0.5. The r value of pi over 2 was 1. That makes sense. I do expect 1.23 to be that. So what it means is that the curve is touching the pole, which is like the origin, the middle. It's touching at 1.23. So if I were to go back to my calculator, just to really understand this better, let's change that to 1.23 for the theta max. Change it to 1.23. Here we go. Okay, it's going to take a sweet little time. And it's moving, it's moving, it's moving. Probably should have made it 0.01, but that's okay. I think because I got a lot going on, my computer probably slower today. Yeah, it's inching closer, and it's going to stop right at the pole. That makes sense. I've done the bottom half of the inner loop. Now afterwards, okay, let's speed this up a little bit. It's kind of driving me nuts. 0.001. And let's go to pi over 2. So it's going to do the bottom half of the inner loop and a little bit to the right of the vertical axis, right? Not that much faster. It's okay. So it's in the bottom half of the inner loop, touches the pole, and notice that there's a little bit of a gap between the curve and the vertical axis, right? It's hard to tell. There's a little bit of a gap there, and it touches this at pi 2 comma what? What's the r value here? 1, right? Yeah, that makes sense. At pi over 2 on the polar axis, the r value is 1. So that's going to help us in the next page of the homework, is seeing that, okay? So then it says, well, algebra determine when it crosses at pi over 2 and 0. Now, at theta equals 0, if you go back to a polar curve, right? Here's a polar axis system. A polar coordinate system. Words. At theta equals 0, that's that horizontal line. What other angle is on that horizontal line? Pi, and 2 pi, and 3 pi, and 4 pi, and onwards, or backwards, right? So yeah, totally what's happening. So when you are asked to find the r values when the graph crosses the line theta equals 0, theta equals pi over 2, at theta equals 0, you also got to do it at pi and 2 pi, because you're told to do this from 0 to 2 pi, right? So I mean, it's kind of redundant to do 2 pi because you're going to expect the same thing, but it's good to say it. At theta equals pi, it's a 4 comma pi. That explains the furthest out it goes to the left, or the outer loop. It goes out that far, the 4 comma pi. When you're at pi radians, r is 4. Now, pi over 2, what are the angles happening at pi over 2? 3 pi over 2, right? They're still in the same line. So you find what it is at pi over 2, which was 1. At 3 pi over 2, it's also a radius of 1, right? Because what's cosine 3 pi over 2? 0. What's 1 minus 0? 1. So 3 pi over 2, my radius is 1. Great. If there is a negative 1, it would jump over here, by the way. So that's right there. So by doing that, now I feel I can, understand this graph better. Hold on, Marie. For part G, the inner loop, we know the bottom half was from 0 to 1.23. We didn't get back to the pole until 5.05. That's when we generate the top half of the inner loop from 5.05 to 2 pi. The drawing is a little confusing, but you can see it generated this first, then this little gap, then the outer loop. Well, then it did this little gap again, and by the time we got 5.5, by the time we got to the origin or pole, what it's called, then we finished off the top half of the inner loop. And that's why it's 5.5 and 2 pi to the top half. Remember, what's your question?
For the question before,
Mhm.
you know, we like plugged in also like
Mhm.
pi and 2 pi. Would we have to do that if it didn't say like on the line of this? Like if it just said
No, it will say on the line.
it will.
Yeah, because I want you to do that because I want you to get a full understanding of the graph. I will ask that. Okay. And then for the inner loop, that makes sense. What's happening now? And again, like in all likelihood, I am gonna meet with Ms. York tomorrow. She's gonna really tell me what she really wants you guys to know about polar functions. And I'm pretty sure she's okay with the calculator part. But I am kind of following her lead in some ways because she does teach this in calculus. So I'm giving you guys the foundational stuff. I mean, granted, we did need a calculator to do this one, but I guess you could have a scientific calculator for this also. But I kind of like the calculator in some ways because the graphic calculator, because you do want to see that motion, right? It kind of helps understand that, right? So because I did a lot of the calculator last year on this test. So I'll let you guys know more details by hopefully tomorrow when I meet with them. Sorry, Wednesday. When I meet with Ms. York tomorrow afternoon. And then finally, how do you create the right side, like that little gap, right? Like this little, it's kind of hard to see. Like this little portion right here, this little portion right there. Or if I go to the TI-4 calculator, how does that get generated? Well, obviously it's touched at 1.23 and it comes out over here at pi over 2. So that little gap to the right of pi over 2, to the right of the vertical axis, happens from 1.2 to pi over 2. And it happens again from 3 pi over 2. 3 pi over 2 is like 4.5 something, right? This 3 has 1.5 times 3.14, about 4.6, 4.7, I don't know. But this little gap is from 3 pi over 2 to 5.05. So anyhow. Yeah. So that's what's happening. So that's the homework, essentially. Good on that? Okay. So it's kind of like the notes in some ways, but we did it for a different graph. Yeah.
So can you explain part 1 and 2?
Yeah. So I already knew that I started at -2, right? And when when the graph was generated, it started at the bottom half of the inner loop. And I needed to know the answer for part E to answer part G, number 1. If I don't do part E, then I don't know how to do it. I need that answer because the inner loop, the boundaries of inner loop is as how far it goes out to the left and when it gets back to the pole.
Oh, so
That's why I need the starting point and I need the pole. That's how you can tell. And then by observing the motion of the graph, it didn't finish off the loop until it touched the pole again. When it touched the pole again at 5.05. And of course, you have to, go back to the starting point. Because think about it. At theta equals 0 and theta equals 2 pi, they're going to meet at the same place. They have to. Because theta equals 0 and theta equals 2 pi is the same thing. That's why we do this also. You start and then here. It's kind of like you're doing a round trip, right? You're, going to San Francisco and you come back home, right? You leave from here, go there, come back. So you're going to come back here. But in between here and here, you had to touch the pole a couple times. That's why you need part E as well. You need both. You actually need both. That's why part G comes after E and F. You need to use both parts E and F to help you with that.
So it's the boundary of just
Yes.
the zeros from F and the zeros from
Yes. The boundaries. Yes, that's correct. Yeah. Right. So that's what's happening there. And we're going to kind of do this kind of same analysis for later in the homework. But now this one here is a fun one. We're going to talk about rose curves. I think we could talk about that today. So we're going to move to that in a sec. Yeah, Marie, go ahead.
The last question,
Hmm?
it says like what ranges of theta produce the portion of the curve that's to the right?
Yes, correct. That little gap, right?
Do you care if we include the like vertical axis or not?
You should include it because it is hitting it, so I would include it. Yeah, I would. Yeah. Um, yeah, I would. Okay. Let's move on to the notes. So just to recap, we did talk about that is old stuff. Here we go. Hold on. What am I doing putting that out? That was dumb. I need to do unit 4. Lovely. My computer's now super slow because all stuff's going on here.
Like when my computer was.
Lecture notes.
Do that. When it's like, these are the same numbers.
Okay, here we go. Yeah, we're gonna talk about hearts and roses. So, this is good. About 3 forms for Valentine's Day. So you could do hearts and roses. All right. Here we go. So we did this example, right? And I did kind of
Pull the cart before the horse. Talking about the whole A and B thing. So they did say like, oh, the length of the outer loop is like A plus B, the length of the inner loop is like A minus, but there's absent values. Let's not worry too much about that right now, because I think we're gonna have another discussion about that later. And actually I have a really good reference sheet on all polar curves, but let's wait till we do more polar curves, and I'll give you this reference sheet. It's just a great, like, hey, here's what to expect about cardio. Like you start comparing. So we just did limicons, right? Now we're gonna talk about cardioids, we're gonna talk about rose curves, and then there's gonna be some other, there's one called a limnoscate and a dimpled heart. There's all these weird names.
by the time we get to the end of the week, I'll give you guys like a little reference sheet of everything. Okay. But hopefully this all made sense, how we found the symmetries, how we did all the stuff. Everything's okay here. Everything's fine. So, all right. Okay. Actually, we didn't quite finish this off. Let me we didn't do where do we leave it off? Did we do part C? Okay, yeah, let me actually do more of this with you guys. So we found, actually let me recap. Let me recap part C, and then I'll do more of this with you guys. Okay, let's recap part C. Here we go. Okay. So we'll recap part 2. Let me get my blog as well. So on page I don't know what page it says, but we're right here.
11.
Okay, mine doesn't say that. Oh, yes, page 11. Correct. Cool. All right. Give me a sec here.
He did it. But now it's like my number 1 song of the month. Are you serious? Yeah. Yeah, I just terrible we got like played up like. Oh,
Good. Okay. All right. So R equals 2 plus 4 sine theta. The graph looked like this, right? It looked like this.
Which makes sense because it's sine, so it's gonna be symmetric about theta equals 5 or 2. The outer loop was 6, inner loop was 2. We had all this stuff happening. We were analyzing it, right?
As we analyzed it, we started realizing, okay, well, what do you notice when you graph it? Only from 0 to pi. And when we started, if I plug in 0, right? If you think about it, what's sine of 0?
Sine of 0 is 0. So what's R value? 2, right? So we started at theta comma, we started at 0 comma 2, theta equals 0, R equals 2, all right? And then when we generate, we went counterclockwise.
And only created the top half, right? So what it really did was this. It started here. And we generate this. Which should make sense, right? Because if I plug in
0, clearly, I get 2. If I plug in pi over 2, what's sine of pi over 2? What's 4 times 1? 2 plus 4. Great, that makes sense, right? Awesome. And when you're at theta equals pi, you're still on a radius of 2. Even though that's -2, it's still a radius of 2.
So it didn't flip over. So it totally makes sense how that graph was generated. So yeah, what do you observe if you graph from 0 to pi? Just get the top half of it, or the part above the polar axis, a equals 0. Okay, now algebra determined the zeros, so set r equals 0, solve it, we worked it out. So what this means is we hit the pole at 7 pi over 6, 11 pi over 6. So when I generate this graph, if I did this in a TI-4 calculator, right? So now we're going to start understanding, without looking at the calculator, this is where I start, right? This is where I start. I'm moving in this direction. So going in this direction. I'm at pi over 2, then I'm at pi finally. But there's a little dip here, right? There's a little dip. Okay. Before I hit the pole, right? I'm not at the pole yet. I've not even touched the pole yet from 0 to pi. I haven't touched the pole yet. Then I'm at pi. Then you got this little dip, right? And when do I hit the pole? Well, that depends on the answer for part C, which is 7 pi over 6. So I don't hit the pole until 7 pi over 6. That's when R is 0. And knowing my unit circle, where else can sine be -1/2? At 11 pi over 6. So once I hit the pole at 7 pi over 6, now I'm trying to generate that inner loop. The inner loop gets generated at that moment when I hit the pole at 7 pi over 6. I don't get back to that pole until 11 pi over 6. So the inner loop is generated between 7 pi over 6 and 11 pi over 6. In between those is when I generate the inner loop. Does that make sense? How the inner loop gets generated, right? So that's how it gets generated, between 7 pi over 6 and 11 pi over 6. So again, this is kind of like, repeating what we did in homework, right? Luke's got a question.
Options, confirm that like the range of values that there's an inner loop is just the when it's first time that's just the one design.
Correct. Yes, correct. That yes. But it was a little different for the previous one where we got the bottom half first and the top half later on. But it does involve the zeros, exactly. Correct. Okay. Now, what's happening when you plug in 0 for theta, or pi over 2 for theta, or other values that are similar to 0? So we plug in pi, and we plug in 2 pi, and we plug in pi over 2, 3 pi over 2, all those different values. Fine. Now, so that should be pretty easy. Plug in 0, plug in pi. If you plug in 2 pi, you still get 2 for r. Whoop-de-doo. Plug in pi over 2, 3 pi over 2, you get 6 or -2. By the way, the inner loop, the top of the inner loop, right here, even though this is at theta equals pi over 2, it was actually at 3 pi over 2. Remember, we're at 0. You trace, you get to pi. The little dip is from pi to 7 pi over 6. Now, before I get to 11, before I finish off this, what's happening between 7 pi over 6 and 11 pi over 6? 3 pi over 2. If I plug in 3 pi over 2, what's sine 3 pi over 2? What's 4 times -1? What's 2 minus 4? So I'm at 3 pi over 2 here, but because r is negative, guess what?
Yeah.
I'm not going to stay there. I got to go there. So that's why that top of the inner loop was determined at 3 pi over 2. I touched the pole, 3 pi over 2, but so actually it was down here, but it got flipped over. And I just keep going. In fact, actually, we have a bunch of negative r values, right? As you should, because you hit the pole there. All the r values are positive until I got to here. Well, actually, until I got to here, and then fine. It's okay. Actually, no, I take it back. It wasn't 0 until I got to here. So I got to the pole. That's 7 pi over 6. Try good.
I was just wondering that on a question when it asks like when the graph passes over the line pi equals theta equals pi over 2, do you also include 3 pi over
You have
2
to,
in that?
yes, because 3 pi over 2 is on that line. Yes, you do. Because it helps with the symmetry part as well. Anna, go ahead. Sometimes it depends. Just wait. Yeah, just wait. Yeah, I know. It seems that intuitive should always be counterclockwise. Just wait till we get to other stuff. The symmetry part's a little complicated. So I'm going to do this with you guys step by step because that's not very easy. So to do the symmetry, I know visually, let me type this up. Visually, we know this graph is symmetric about theta equals pi over 2. We know that, right? But we must prove this. But we are asked to prove the symmetry. 12 now. Algebraically. Okay, fine, let's do it. So remember, replace theta with negative theta. So R equals 2. Now this is where it gets weird. R is going to equal 2 plus 4 times negative sine theta. Sine negative theta is negative sine theta. Do you guys remember that? Yeah. So R equals 2 minus 4 sine theta. Well, here, this is strange. This is strange. Why is it strange? Because R should now be negative R. Does that make sense? Or did that confuse you guys? Yeah. So or R should equal negative 2 minus 4 sine theta. You know, when you change R from itself to negative R, you need all the signs to change. Even the 2 has to change sign from positive to negative. But that didn't happen. So sometimes you will run into that situation where replacing the negative theta doesn't work for us. We have another way to prove the symmetry. What was the other way to prove the symmetry? Replace theta with what? Correct. So in this case, try the alternative. What's the alternative? You replace it with pi over 2. So pi minus theta. So I'll do it over here. So I'll do it again. What was the question off to the right? Emily had a question? You end up with negative 2 minus 4 sine theta. I didn't get that. I did not get that.
But doesn't it when you get when you plug in the negative one and then it's the same thing, doesn't it mean it's symmetrical about the polar axis?
Right. If it was exactly the same, it would, but I know graphically it's not symmetrical with polar axis.
So could you know that won't work? Like,
No, right, but no, I plugged in, I was hoping when I replaced it with negative theta, that it would be negative R.
yeah, when
Right. Right, correct. Now, here's just to really mess with you guys. When you replace theta with pi minus theta, I'm not looking for negative R, I'm actually looking for R. I know. It's crazy. So I'm looking for this to be unchanged. Now, I know you guys are not gonna like me. What do you think we have to do to verify this? You guys remember? I know. You guys use a difference formula. Sorry.
Every time you do it, or only like.
Oh, minus. Worse. Wait, so are we gonna be given these formula tests?
Everyone but you, since you asked. So sorry, Lucas. Don't ask those questions anymore. I'll take more forms away from you. Yes, I'll give it to you. Don't worry. Now if I work this out, it's not too bad. I think that's be okay. What's sine pi? What's cosine pi? And the minus negative? So does it stay unchanged? It does.
Goes like that, went away. Cosine pi.
0 times cosine.
Oh, it's 0.
Yes, circle, guys, this circle. This circle.
Plus.
Yep. Wait, this circle.
Theta.
Oh.
Oh.
Cosine pi is 0. Anyhow. So the symmetry is kind of funny. So for symmetry of pi over 2, there's 2 ways you can do it. Replace theta with negative, well, you're always gonna replace, well, sorry, not always. Replace theta with negative theta. If the final outcome is negative r, cool. The final outcome was not negative r. So there's another alternative, yes. Replace theta with pi minus theta. If the final outcome is r, cool. It's sort of pi over 2. And that's what happened.
What if neither happens?
Then there's no symmetry, or then you messed up. Because we see it's symmetric. So go back and check your work. Yeah, go back and check your work. Yeah, I think that's why we allowed the calculator, because I know to give that safety net. Kingsley, go ahead.
So like for both methods, if one doesn't work, we just do the other.
Correct.
Okay.
Yeah, and by the way, the notes here do explain that, right? And the notes here, we explained there are 2 methods here. For each polar axis symmetry and theta equals pi over 2 symmetry. So for theta equals pi over 2 symmetry, you do this way, which is the easiest way to do it first, but if that doesn't work, then how to do this way. Now for theta equals 0, the polar axis symmetry, replacing theta with negative theta to get r, cool. If we don't, then you do this one, but then it becomes negative r. And we can actually verify all this stuff, because if I were to plug in theta, if I did plug in pi minus theta, that I would get negative r eventually if I did the difference form for cosine. First page. Yeah. Or page 9. Okay, so I want to make sure we had that discussion. Okay, so now we've established symmetry. Now I think we're okay. We established the symmetry. Let's move on to cardioids. Now we can do cardioids, all right? All right, cardioids. So let me show you what's happening here. So I will tell you this. These 2 values will always be the same, or they'll be opposites of each other. So the absolute value, if it's A and B, the absolute value of A will equal the absolute value of B. So say it's like 4, negative 4, 2, negative 2, 1 and 1, 3 and 3. That's what's happened. And I'm just gonna show you the graphs. We're not gonna go to Desmos in interest of time. I know you guys can do this. So there's no inner loop, by the way, because absolute value of A and absolute value of B are the same. Absolute value of A is the number that's off to the side. The absolute value of B is the number in front of the trig function. Like this here, right? AB cos theta, AB sine theta. If these absolute values are identical, then no inner loop. No inner loop. So here are the sketches. Okay, here are the sketches. So let's kind of, I'll let you guys copy this down. So you're making like these terrible looking hearts or tomatoes, maybe. Maybe like green tomatoes. I don't know. These are like maybe if you're growing like not terrible ones, but
I really do. want to
typical Roman tomatoes or you stick on it. Anyhow, yeah, so what's happening here? It's 2. So I think 2 kind of makes sense because I'm doing 1 plus 1. Because if you plug in 0, cosine 0 is 1, so that makes sense. And so that's where it starts, by the way. It starts here. And if I plug in pi over 2, I get 0. So it looks like it's going counterclockwise. And then you have the little gap here. By the way, if I plug in pi, what's cosine pi?
Negative.
Okay, so the R value is 0. So get back to the pole there, right? Then I have this other little gap. If I plug in 3 pi over 2, that's 0 for cosine, so 1 plus 0 is 1. But then I finish it off by coming back this way. Right? Finish it off. So basically it does this. We start here. Start. And it kind of does this.
That's the motion it goes through. Exactly. All right. Depends. Depends what you got. Depends. Let's see here. So what if I plug in 0? So it's starting here. This is where I'll start. Yeah, the R value is 0 at 0. Yeah, because cosine of 0 is 1, 2 minus 2 is 0. And it's going to go like this. So it's still going to go counterclockwise until I get here. See, notice we have 4 as the width, which kind of makes sense. And also we notice it's going counterclockwise. It's going to the left. Okay. So then you have negative in front of B. It's going to the left. The little gaps between the curve and the vertical axis. Looks like that's probably being determined by that number. Looks like that number determines it. Did we notice that I think previously the other problems? Yeah. Yeah. I think that number, the A value determines where it touches that vertical axis.
The start is the sum or difference of the coefficient.
Correct. Correct. Yeah, coming back, just I know I'm jumping around a little bit, but yeah, notice how like at 3, that's where it touches the polar axis over here. Yeah, that makes sense. Yes. All right. So we have this. Okay. That works. Whatever you want to call it. Okay. And then for sine, that's vertical. And if I plug in 0, I do get through. So I start here. And we're going like this. And we touch the pole at 3 pi over 2. Because sine 3 pi over 2 is -1. 3 minus 3 is 0. So we touch the pole. Oh, plug in 0 for theta. Always plug in 0 for theta. That's where you start. And find the R value there. And here, I start over here. So I'm starting. And let me think here. If I plug in, yeah, it hits a pole. That's at 0 comma pi over 2. Because you're plugging pi over 2, your R value is 0. Because sine pi over 2 is 1. And 4 minus 4 is 0. So it's going like this. Yeah, so it does that. Yep. Okay. We're going to analyze one of these in just a moment. Yeah, go ahead.
Right.
Sure, of course, yeah. Okay, let's keep moving. Hope you're okay so far. Okay, just observe. Look at the 4 graphs. How do sine versus cosine affect orientations? Cosine's up, down. Cosine's left, right. How does the plus or minus affect the graph? The plus means we're going up or to the right. Minus means we're going left or down. We'll take a close look at 2 minus 2 cos theta. So 2 minus 2 cos theta was the second one we did on the previous page. And let me redraw it for us. It's not too bad. Kind of looks like a heart. All right. Okay. Okay. So that's how the curve is generated, right? Now, if you only go from 0 to pi, remember, we started here. This is where we started, right? And remember, we went counterclockwise. And this right here was that, so that was 0, 0. And that was at 4, pi. So when we go from 0 to pi, that's only the top half, right? Only the top half is generated. Okay. Now, analytically determine the zeros. Plug in 0 and pi over 2. Figure out when do we create these other things here, and let's do the symmetry. So I'm gonna have you guys go through parts 2, 3, 4, 5 of part C. So algebra determine the zeros, find where the graph, blah, blah, blah. Find some other stuff, find the symmetry. And then I might jump to Rose curves after we finish this, because I do need to talk about that. So that's important. So yeah. So go and try the other parts of these notes. I'll walk around, help you guys out. So go and start over here. I'll turn this off for a moment. Okay, so replace R0, solve. Tell me where you're touching the pole. Again, plug in 0 for theta, and also pi and 2 pi. Plug in pi over 2 and 3 pi over 2 for theta for part 3. For part 4, they're asking you when you're to the right of theta equals pi over 2. You should be able to figure that out. State the symmetry. That should be pretty easy. And then we'll discuss in a few minutes. So I'll have you guys do the next few parts on your own. We'll look at the homework right now, see what's should make sense.
How does the sign?
So it crosses the and it crosses, but they weren't positive, but they're zero.
There's no instinct when we come to see that, but Emerson and all I don't have that. I don't think it's called. I'm guessing. Huh? I'm guessing it's the secret one. They were like, what's yours? So we're the secret. I was just kind of a secret. I was like, okay, well, I'm not playing it. It's a secret. I'm afraid. It's so funny. Just embarrassing. Wait, do you like this? Yeah. I actually founded that last year, but I'm not really about this year. I'm not a founder. Well, yeah, remember when I went to BC randomly for last year? That's like that group we created together for this. But in case it's terrible, just know I haven't worked on it. So what are we gonna do? I'm not sure. It's like stations. I think they're fine. And the groups are totally randomized and find all the grades. Not random. Because it's like student choice. Yeah. No, but like, this is random, like, see, are there like seniors, freshmen, and I think so. Yeah, that's probably, yeah, most seniors. This is not what I like. Yeah, because it came from, because my old school, we used to do this, these little tiny part. We're like every month, like hit from like each grade, obviously I went to like a tiny school, so like we had one kid for each grade, like from K through 8. And you had like a state name, that was your group, you would meet once a month, which is saying, like, it would be like, the name of your group was named after my name. Okay. So I was just like, Ignatius, so that was like our group. And then we were just like.
Okay, let me show what's going on right now.
I have.
Okay,
She's like one. I'm sure that'll be more like yeah. We're just being way too many good.
hopefully getting this so far. Plug in 0 for R, work it out. Should get close to equals 1. That happens clearly at 0 or 2 pi. So that works there. Obviously, replace theta with 0, pi over 2. If you place it with 0, you should get 0, 0, which we know. If you place it with pi at 4, pi, which you know is the outer far off to the left. And of course, if you plug in 2 pi, you should get back to 0 for R. If you plug in pi over 2, you should get 2. 3 pi over 2, you should get 2 again. And that helps us generate yeah, it helps us generate these parts right here. Right. Okay, hopefully you guys are okay with that. The substitution. Then for 4,
We can go back up.
sure, no problem.
So, just the kill it. Like, perfect. But they're gonna be bored. Like, something like, that's so embarrassing. Like, if they're gonna be born like 20, 30, like 7 or like, yikes. So much more, like you missed everything.
Okay, we're cool?
Yeah.
All right. Then for 4, when it asks you find the range of values of theta that produce a graph that's to the right of theta equals pi over 2. So let's come back to the graph again, right? So if if you want to be to the right of the vertical axis, so we started here, and we've got that little part from 0 to pi over 2, and then we did a bigger part from pi over 2 to 3 pi over 2, and we got this little portion from 3 pi over 2 to 2 pi. So to answer that question, I would say from 0 to pi over 2 and from 3 pi over 2 to 2 pi. After I've done parts B and C, right, or parts 2 and 3. So in order to state that, okay, justify the range of values of theta that produce the part of the graph that is to the right of the line theta equals pi over 2. So remember, at theta equals pi over 2, the point's at 2 comma pi over 2. At 3 pi over 2, the point's at there. So that's why we could state the 2 intervals are this, that, and that. So those little portions right here, that right there was from this, and that one was from that. So 0 pi over 2 got me the top half of that portion, and 3 pi over 2 got me the bottom half of that portion. There's a lot of explanation here. Don't feel like you have to write that per verbatim. I think what you just have to really be present to is that at theta equals pi over 2, we have that point. Theta equals 3 pi over 2, we have that point. And of course, we touch the pole at 0, 0, and 0, 2 pi. So really, it's, as we said, like it's gonna be that boundary, right? As Lucas was saying, it's that boundary from the pole to when we're touching that axis. So that's what's happening there. Hold on, Marie. And then for part 5, yeah, just replace it's pretty obvious it's symmetric by theta equals 0. So replace it with negative theta. Comes out nice and clean. R value stays unchanged. So you get your symmetry there. That's pretty easy. But for 4, Lucas, what's your question? And I see Emma has. Oh, he had a question. I'm sorry. I don't know why. But Mary had a question. Sorry. Yeah.
So for 4, when it's
Lucas has so many questions. That's why I assumed. Yeah.
justify your answer, do you just want a few notes like to show that we know what's going on?
Correct. Correct. Right. Yeah. Yeah. Okay. Emma, good.
Always be like some combination of like pi, half.
Correct. Yeah. Correct. Yeah. Just depends on the symmetry that's happening too. Yeah. Correct. Yes. Yes. Yeah, I mean, it depends. I mean, we did have like that 1.235.05 in the homework. So yeah, pretty much, yeah. Okay. In the interest of time, and these, the other parts of the notes will go by a little faster. So again, glad we're taking our time. We're not rushing, but we got about a few more minutes left. I don't want to do dimple limicon or convex limicons. Here's how those look. They look like this. Look like these blobs. We'll save that for Wednesday. And a lemniscate looks like, I think, like a figure 8. Like kind of like infinity symbol. I want to jump to rose curves. Let's jump to page 17. Yeah, just to talk about that. We're not going to spend too much time on it, but just so you at least understand what's going on. Okay, rose curves.
Here's what's going on with rose curves. And again, you can use Desmos in your calculator to kind of explore. But what's going to happen is you're going to have sine, cosine, obviously. You're going to have a number in front of theta. So they will have coefficients. And whether it's odd or even does matter. I'll show you the diagrams in just a moment. So it's going to be a lot more observation. The number in front of sine and cosine is also going to tell me the length of each rose petal. So let me show you the first two with cosine.
And okay, we're kind of rushing this a little bit. So we'll spend more time on this on Wednesday. Let me talk to Ms. York. I want to see what she wants.
Sure.
So I don't know yet.
Wow.
Okay.
So now, this is where it gets a little funny. If the coefficient of theta is even, okay, if the coefficient of theta is even, you'll double the number of petals. So notice like I have cos 2 theta, that generated 4 petals. But notice that when I have 2 cos 3 theta, that only generated 3 petals. So if you have an odd number in front of theta, you'll have that many number of petals. If you have an even number in front of theta, the double of that number will be the number of petals. Also, the first petal is always on the polar axis. The first petal is always on the polar axis. Also, look at how the petals are oriented. The symmetry, right? If you have 3 petals, what's 360 divided by 3? 360 degrees divided by 3. So 0, 120, 240, back to 360. You have 4 petals, right? You have 4 petals with 360 divided by 4. So 0, 90, 180, 270, back to 360. And the length of the petals is determined by the number in front of cosine or sine. So like that's 2. So length of petals is going to be length 2. We will actually do a table and do this more slowly on Wednesday. But if you graph this in a calculator or in Desmos, you'll see it's happening. In terms of the order in which it does it, that's not going to be terribly obvious. And that's where we'll have to take more time talking about that. And maybe slowing it down a little bit on Wednesday. Also, if I show you the sine curves. Now, sine's kind of funny. It's still the same thing. If you have an even number in front of theta, you double that. So of course, if I have 4, I have 8 petals. If I have 5, I have 5 petals. Now, the symmetry is a little funny, and the way it starts is a little funny. I'm gonna hold off on explaining why it does this, but if you do think about it, 365 by 5 is 72. Each is separated by 72 degrees. But why it starts there, I have to save that for Wednesday. Obviously, you have 8 petals, 365 by 8 is 45 degrees. Each of these petals is separated by 45 degrees. And I'll wait. Have that discussion with you.
Wait, so 360 divided by the number of petals is not part of it.
Correct. Right. Yeah, so we'll hold off on that. So for the homework, I'm gonna have you try pages 3 and 4. I think you guys will be okay. If you get stuck, that's okay. It'd be a great way to discuss. So I'm gonna have you do just pages 3 and 4 of the homework. Doing a little exploration. So you might get stuck, you might be a little confused. If you're confused, that's okay. If you don't submit the homework by Wednesday, that's okay also. But just try it. We'll have a discussion about it. It's good to struggle a little bit, and then we'll be able to close the loops. These are all loops. We'll close these loops. Okay.